Okay, welcome back everyone. In this video we are going to continue talking about electric potential energy, and in this video we want to talk about equipotentials. So what is an equipotential, or sometimes it's called an isopotential surface? Well, an equipotential surface is a surface with the exact same value of the electric potential everywhere. That kind of makes sense. So if the electric potential is V, that means that V is a constant value at every point on this equipotential. All right, now the most important characteristic of an equipotential is that the surface is perpendicular to the electric field lines. Now let's think about why this is the case, and we'll see a lot of this. But let's say that I have potentials that go like this: 0 volts, 5 volts, 10 volts, and so on and so forth. Okay? And let's say that in this case, we know that the electric field is actually going to be pointing from high potential to low potential. Okay, so the electric field will actually be going this way. Now, why is the field pointing to the left and not to the right? Well, if you think about it, earlier we mentioned that E was equal to negative dV dr, and we'll come back to this, and this comes from the definition of the change in voltage as being negative integral of E dot dr. So these two are kind of interchangeable. So what that says is that, and here's another way to think about it. If I put a proton here, this proton would feel a force with the electric field, so also going to the left, and it would then go from a relatively high potential to a relatively low potential. And by doing that, its electric potential energy would decrease. Okay? So since delta U is negative, delta V is also negative for a positive charge. Now we're going to be investigating this when we do some labs a bit later on. So what's the equipotential surface look like if you just have a point charge? So here's a point charge, and here's one equipotential. Okay, it looks a little bit off, but not too bad. There's another one, and another, and so on and so forth. Okay, so if that's the case, what do the electric field lines look like? There they are. So the electric field lines are going radially outward for a positive charge. We know this already. And because of that, the only thing that can happen to give perpendicular equipotential surfaces is if we have circles. Okay, so our equipotential surface is a circle. So here's one example problem. Find the potential at a distance of 1 centimeter from a proton. Repeat this for an electron. So there are a couple of ways to think about this. We could start with the value of the electric field and go from there. But probably the easiest thing to do for a point charge is just to realize that it's equal to kq over r. So 9 times 10 to the 9th, 1.6 times 10 to the negative 19th coulombs, and r is 0.01 meters. So that's just 1.4 times 10 to the negative 7th volts. Now for an electron, it's the same thing, but you get a negative sign on the charge. So for the electron, here's the proton. For the electron, you just get negative 1.44 times 10 to the negative 7 volts. Okay. So let's go back to what we were talking about a moment ago. Let's talk about equipotential surfaces. So if we have parallel plates, like so, then we're going to have an electric field which goes from left to right. Okay, so again, if I put a positive charge here, it would feel a force to the right. It would get repelled from the positives and be attracted to the negatives. Now, we said previously that means the left side is at high potential or voltage, and the right side is at low potential or voltage. And again, this all goes back to the fact that if the charge is positive and it's moving along the electric field, positive work is being done. So that means the change in potential energy is negative. Now, because this is true, the change in voltage is also negative. So it's going from a greater to a lesser voltage. Now, in between, we can label this with equipotential surfaces. Notice that the surfaces are everywhere perpendicular to the electric field. And also notice that if you took these lines, the electric field lines, and you made them radial, then these purple equipotential surfaces would start to curve around and make the spheres that we saw earlier. So if I move a charge from point A to point B, then I can really talk about the potential difference from point A to point B. If I go from point A to point C, it's going to be the exact same result, okay? Because the movement from B to C, which is perpendicular to the field, isn't going to change my potential energy. Here's another way to think about it. If point B and point C are on an equipotential surface, they're at the same potential, which means that from B to C, delta V is 0, which means delta U is 0. There's no energy change from one to the other, so that means that the work done going from B to C is also 0. Remember, you're going perpendicular to the field, so no work is done. So what happens to this test charge that we talked about at point A? Well, if we release it, it's going to move this way, and the change in potential energy and change in potential will both be negative. And it doesn't matter, again, which way we move. If we go to B or C, we're going to end up with the same result. Okay, so here's another example. Let's say we have 2-point charges. So I think it's time for a different color. Okay, so we have plus 5 nanocoulombs and negative 3 nanocoulombs separated by 35 centimeters or 0.35 meters. What's the potential energy of the pair? Okay, so potential energy, remember, is K Q1 Q2 over R. Okay, and so that's 9 times 10 to the 9th, and 5 times 10 to the negative 9th, and negative 3 times 10 to the negative 9th. I'm being really bad with units, but that's coulombs and that's coulombs. And R is just 0.35 meters. It's not squared. So the potential energy of the pair, you can calculate this out, is about negative 1.1 times 10 to the minus 6 joules. Why is it negative? Because you have a positive and a negative charge. Okay, what is the electric potential, V, at a point midway between the charges? Now, potential is different from field, okay? It's different from energy. To find the electric potential at that point in the middle, I'm going to have to add things up. I'm going to have to do K Q1 over R1 plus K Q2 over R2. Now, since we're in the middle, R1 and R2 are the same. It's just 0.175. So really what we're talking about here is K over R times Q1 plus Q2. And when we plug and chug that, that's 9 times 10 to the 9th over 0.175 meters times 5 minus 3 nanocoulombs, which is 2 nanocoulombs. And when you plug all this in, you get 103 volts, and it's positive. Okay? So the way to think about this is that the positive 5 nanocoulomb has more an effect than the negative. So that's our answer here. Okay, now, how do we get the electric field from the potential? So there's a lot going on here. First, we know that delta V is equal to negative E delta R, where this is a uniform field. We talked about this previously. If it's not uniform, then we just break it up into pieces. And so dV is equal to negative E dr. So this is non-uniform. Okay, so that's a non-uniform. So that means that the component of E in the R direction is negative dV dr. This is a very, very important one. I can't tell you how many tests and quizzes I've graded that students forget about this negative sign. Don't forget about that one. It's crucial. And apparently I can't write an N. Okay? So, what's the last thing here? Well, this is something kind of weird. This is called the gradient. And we saw this before when we did potential energy related to force in the mechanics part of the course. But we can calculate the electric field if it has components by taking the partial derivative of V with respect to x, and that will be our component in the I hat direction. Okay? So this is what we call the gradient of V is equal to E. Okay? So that means that what you do is you take the partial derivative of V in the x direction, and that's I hat, and similarly for J hat and K hat. Okay, so this last point got cut off a little bit, but it's very important. It says that the electric field is strongest where the potential is changing most rapidly. And how do we know that? Because we have this expression right here that says that E is equal to negative dV dr. So the quicker the potential is changing, the greater the field is. Another way to think about this is that the more bunched together the field lines are, or the potentials are rather, the stronger the field is. Okay, so here's an example of how to deal with this. Okay, so here's a one-dimensional case. We have electric potential, and we want the electric field. Okay, so remember, E is negative dV dr. So it's negative, and then we take the derivative of V, which is going to be negative 9, and then we have minus 6x. I'm leaving units out. So that's going to be 9 plus 6x, but we want to evaluate this at x equals 2, so E is equal to 9 plus 12, which is 21. Now we put the units back in, it's going to be volts per meter, and because we have a positive sign, our electric field is in the positive I hat direction. Okay, so far so good. Let's do one more example. This will be a two-dimensional example. And now we have a region of space where the electric potential is a two-dimensional function. It depends on x and y. So we want to derive the vector representing the electric field at the point 1, 2. So what we have to do is we have to apply the fact that E is equal to the gradient of V, which means that E is equal to negative partial derivative of V with respect to x in the I hat direction. minus partial derivative of v in the y hat, with respect to y, in the j hat direction, and if we had it, it would be minus partial v partial z in the k hat. But to keep things simple, this electric potential is only v of x and y. Okay, so we don't have a z hat component or a k hat. So the electric field, generally speaking, is going to be negative. And then what's the partial derivative of our function with respect to x? Well, it's going to be negative 3 plus 6y minus 4xy. And that's all in the I hat direction. Okay? Put a negative sign. What is the partial derivative of our potential with respect to y? Well, the first term is going to give us 0. Second term will give us plus 6x, and then we're going to have minus 2x squared, and that's in the j hat direction. Finally, we evaluate this at the point 1, 2, and so that means that the electric field is, well, let's distribute all of these negative signs. Okay? So we're going to have 3 minus 6y, which is 2, plus 4xy, which is 8 in the I hat direction. 3 minus 12 plus 8 is negative I hat. And we don't have units, but we would just assume that it's something like volts per meter. And then we have negative 6 times 1 plus 2 times 1 squared j hat. So that's negative 6 plus 2 would be minus 4 j hat. And that would be our value of the electric field. So how do we draw it? Okay, so here's our coordinate system. Here's the point 1, 2. And we know that to get the electric field, we have to go negative 1 I hat and negative 4 j hat. So that is going this way. That is our electric field vector. Okay? So the takeaway from this is that if you want to get from the potential to the electric field, it's a very easy relationship. E is negative dV dr. So keep this one in mind. Okay? We will be using this one a lot as we go through the remainder of the course. Next time we're going to talk about how to start calculating the electric potential of charge distributions, which will be not too unlike when we did this for electric fields.